Okay, what we're going to discuss is some things related to the design process, particularly in the early phases of the design where we're at now, this preliminary stage. We're trying to nail down different ideas and which of those ideas may be beneficial to the particular design or mission that we're looking at. So first off, what we want to do is try to answer this question: how do we make the best aircraft design? How do we come up with the best aircraft design? To do that, we really need to first answer these questions. The first one is, well, what do you mean by best? You have to come up with some quantitative or qualitative measure about what you mean is a best design. So that way, when you have two or more competing designs, you can then determine which one of those is going to be better. The second is, how can you estimate value so that we can compare the two designs in some quantitative, meaningful way. And what do we mean by quantitative? Well, as opposed to qualitative, where we say, well, yeah, I think this one's going to be a little bit better. This one seems like it's going to be faster. You really have to have some kind of number that justifies your decision process. And that allows you then to say definitively that design A is going to be better in this way, in this particular metric, than design B. And then finally, how do you select these design variables such that you can then optimize a design? So you have several different parameters, you're able to quantify those, and then from that you can determine what the optimum combination of those variables are going to be. You have to do these. You have to do number one before you can do number two, and then you have to do number two before you get to number three. So you have to be able to really answer these in these particular stages. Now, keep in mind that at different stages of the design, we're going to have different hats on. Sometimes we're going to be thinking with our subject matter expert hat on. So we may be thinking, for example, I need to focus on, making the aerodynamics as good as possible, or the structures as good as possible. And that's really where it comes in from a team standpoint. So you're on your sub-team with that particular specialty. But ultimately, what we want to be able to do is find the optimum combination of all these different best capabilities for all these different pieces that we have, and put them together for one good overall design. And so that way our final product may not be the best it could be in terms of aerodynamics, but it's good compromise between all of these different competing elements. Now, keep in mind that when we say best design, there's not necessarily going to be a right answer. So I'll harp on this a lot. There's no, magic or silver bullet. You have two different teams that have the same different amount of information, the same expertise. They can come up with two different designs that may be equally good in most respects. So here's an example of that. This was one of the senior capstones from Design Build Fly 2008. This had a particular payload mission associated with it. Notice they each had to carry a number of bottled water. And so they were essentially designing the vehicle around the payload, but their other constraint that they had was that they had to fit in a certain rectangular box. So you could trace out this 4 by 5 foot box on the ground, and so then you had to come up with an option of, well, am I going to fit the wingspan within the short side of that box or the long side of that box, and how does that impact my design? So you can see the teams have very similar payload compartments. How many different ways can you put these bottles of water in there? And they had to be individually spaced, just like you would do with a passenger aircraft. But the other elements are pretty different, right? The propulsion systems are similar. They're both using tractor system designs, but the tail and the wings are both different. So one of the things that I always like to illustrate on this one is the orange team, rather than looking at the constraint from, well, are we going to put our wings in the short side or the long side of the box? They said, yeah, we're going to put our wings to the diagonal. We're going to try to maximize our wingspan as much as possible. So we're going to rotate our aircraft so that way we get a little bit of extra span. Now, doing that meant that part of their tail, if they went with a conventional tail, would have been outside the box. So they had to go with this asymmetric tail design, which actually worked out really, really well. Other examples, VTOL aircraft, kind of going through the stages of the VTOL concept. We know that this is something very desirable from a fighter aircraft perspective, regardless of what type of, fighter aircraft configuration that you're looking at, whether it's air superiority or ground support, having this capability for a single point takeoff and landing is highly advantageous. There are different ways to achieve this, none of them really successful until we get to the Harrier here shown in the lower right hand corner. But this design, because of this particular constraint, also means that it's not good in really an air superiority role. Now look at the comparison between these two. Contemporaneously we have the AV-8 and the F-104. They have pretty close maximum takeoff weights. They have pretty similar thrusts, but notice that the Harrier actually has more total thrust than the F-104 does. But since you're putting this constraint for this vertical takeoff and landing capability in the design, it constrains you in other ways, primarily in your top speed. The Harrier is subsonic, while obviously the Starfighter is able to go supersonic. This just illustrates the point that you can't have everything. There are going to be trade-offs that you have to give up and make during your design process. So what are you going to focus on? What's important for your particular design? Another good example of this is the Joint Strike Fighter competition, shown here with the Boeing and the Lockheed Martin entries into this particular competition. Again, same mission, but they ended up having different solutions to the problem, and thus different design focuses. And we'll come back and talk about this one more in class as well. Now, that said, there are lots of different options to do this, right? We've talked about this in class before, where you have many ways to solve this problem. Each one of these could be valid, but what you want to do is try to narrow down your design space as much as possible by really lumping these together, looking at the particular constraints. Which one of these can you rule out early on in the design process based upon your mission and your other design requirements that you have? Then you can start to look at these in a more quantitative fashion, so you can compare design number 1 with 2 with 3 all the way up to 45 and start giving them some kind of objective ranking that allows you to compare all these designs in a quantitative fashion. Now, unfortunately, in the kind of day-to-day engineering world, most of our design decisions are made by an approach we like to call BOGSAT, which just stands for a bunch of guys and gals sitting around talking. That means you have people in a room. Ultimately, they're going to be the ones that make the decision on that particular design, and it's the discussion that typically drives these, as more than they should. So what we want to do is try to come up with these different types of tools or methodology that gives us a greater engineering foundation throughout this design process. Now, as a reminder, there are different design phases. We're in the conceptual design process right now. This really kind of handles those basic mission requirements, looking at the basic performance. And we're looking kind of a gross geometry, right? We have the overall configuration of the platform and placement and capabilities. Now, we'll be going through this and we'll get into a little bit of the preliminary design. I would say not quite halfway through. There are going to be some detailed design pieces that we're going to make, but not all the way through. Now, obviously, when you say get up to the senior design phase, you actually have to build something, or you're developing a real product post-graduation, then you have to go through all of these. Now, there are different pieces of this, and you might just have the same team feed through, Or you might have a conceptual design team that once they're done, they throw stuff over the wall to a preliminary design team, that then once they're done, they throw stuff over the wall to the detailed design team. Or you might just be able to carry this from all the way from conception to birth. Now, one thing I like to emphasize is that we're taking a kind of a nonlinear process as we go through this. We're talking about aerodynamics, then performance, and then propulsion, and stability control, and structures, and all these pieces. At the same time, what we're doing is talking about the design process. So this lecture really focuses on that design piece, primarily the benchmarking side. While at the same time, we also have to consider the physical constraints dictated on the design by the laws of nature. This really kind of helps us, get a handle on what's going to work and what's not going to work when we come look at the options that we have on the table to meet our specific mission requirements. So first thing are trade studies. So here's our YF-22 and our YF-23. You're looking for an air superiority competition, and both of these aircraft, again, designed by different teams to solve the same mission. So you end up with a lot of common elements. Some of these are going to be driven by the design requirements, the mission requirements, or I should say the RFP, saying, yeah, we want to have 2 engines. So that way if we lose an engine, then we don't have to worry about the risk of the aircraft. And so that's imposed upon the design. Then you have performance requirements, and well, we want you to have a max speed of 1.5 Mach number. Then you have basic physics in terms of being able to lay things out, where the wing's going to go, where the tail's going to go, and then things are really kind of driven by the systems engineering process of putting everything together, that the cockpit really has to end up being up front. There's nothing that really dictates that, other than trying to lay everything out and making sure you kind of meet those visibility requirements for the pilot. But there are also a lot of subtle differences between these two designs. So what a trade study does is it allows us to compare one design option with another. Now the great thing about trade studies is you can use these across the entire design process, from basic component selection to materials, all the way to the vehicle concept. And that's essentially where we're at right now, is trying to use a trade study to compare one concept with another concept. All we're doing are looking at pros and cons for these. We come up with a list of different performance parameters, and we compare one concept with another concept. Now, these trade studies can be quantitative, meaning you assign numbers to them, or they can be qualitative. We kind of use a combination of the two. You have to be really careful when you start weighting trade studies, so you're giving different values or importance to different parameters, because that essentially allows you to put your finger on the scale and say, well, I really like this design, so I'm going to make this performance parameter that rates really highly in this particular design much better, or give it much more weight than some of these other parameters. So you have to be really careful with that. So you want to make sure that you're trying to be really fair and objective when you go through a quantitative analysis. So here's an example. Again, not looking at any particular design. We have design 1, 2, 3, 4, 5. In this case, what we're doing, we're choosing design 1 as a baseline. This is usually pretty useful if you already have a concept in mind, or you're comparing it with another design. So you can think about this as an evolutionary process. So in this case, you're looking purely subjective and say, hey, for all these parameters that we have on the left-hand side, our baseline, that's where we're starting from, and then we look at each other design, 2, 3, 4, 5, we look at each one of those parameters and say, well, is it substantially better, or is it substantially worse in this particular performance area that I'm looking at? Then you can sum all those up, weight them, and then come up with a final number. So in this case, you can look at it and say, well, obviously design 2 performs a lot worse than design 1 but design 3 appears to perform better. And again, note that there's no weighting here, so that way you're not necessarily putting some of these performance parameters more important than other ones. A lot of this is really kind of based upon subjectivity in terms of which ones you think are going to be important in terms of your design parameters, but also some intuition. What through your experience do you know is going to be important for a particular mission. Here's another example. This is looking at wing in particular, so rather than looking at, say, specific type of concept or plan form, now what we're doing is saying, well, we want to design our wing. We'll look at our wing plan form. So what are the different design parameters that go into our wing? So for example, we have sweep, aspect ratio, wing area, wing thickness, and wing camber. How do each one of these design parameters impact specific performance specifications? So all these things over on the left-hand side. So for example, we could say, hey, we know that a swept wing gives us a lot of great capabilities in the high Mach number, but it really degrades performance across the range, in terms of our other areas. And so aspect ratio, which is great for high lift drag, is bad for high Mach number. Likewise for overall wing area, where we could look at other competing parameters and say, hey, if I want to really focus on my takeoff and landing distance, sweep isn't so great, but all these other things are. So now you have two of these that are really combating one another directly. So how do you deal with that, and how do you determine which one of these is going to be more important for the design that we're currently doing? Now you have lots of different configurations, lots of different options in aircraft, so you really have to start laying things out and then coming through the process and determining some subjective and objective type of quantitative measure to make these determinations. Tail types are a good example of that. How do you determine which one of these tails is going to be particularly better for your aircraft design? Some of these are going to be pretty common, so when you look at a conventional T-tail or cruciform tail, they're kind of minor changes, but some of those could have a real performance impact on things such as stability, control, weight, and or safety on your particular aircraft design. Ditto for landing gear. You have a lot of options in how you're going to lay your landing gear out. So you have to make that determination about which one is going to fit your particular design, and again, come up with an engineering justification for why you're making that particular selection. Now, we have to remember that in this particular process, when we're going through this conceptual design phase, that when we come up with a concept, it's not necessarily going to be the final design that makes it through this preliminary and detailed design phase. SR-71 is a really great example of that. Again, the first one the first design did not meet the overall mission requirements and the specifications that were laid out for this particular aircraft, and so they iterated the design. And what you'll notice as this design evolved, there were some features that would be carried over from each design iteration, and then they would discard others. And so you kind of end up with this evolutionary process where some of the good things stay, maybe they go away for a little while and then come back, but it allows you to start looking at all the different options that you have until you come up with your final design choice. In this case, A12 was the 12th design iteration that they went through before they finally landed in the concept that would solve their particular problem that they have, which obviously ended up being in one of the greatest aircraft designs of all time. Now, looking at the trade-offs, again going back to the YF-22 and the YF-23, there's certainly, so the 22 obviously won the competition, but there are still things that the 23 was better at. It had better aerodynamic ruling. It was a real hot rod, so it had a better top speed. There's indications that it had better performance metrics in terms of turn rates, and, combat maneuvers. Not all those numbers were released, but there are certain things that the F-22 certainly excelled at from an avionics standpoint in terms of the platform. So in terms of being able to put more payload on board and be able to store everything internally. You can still argue, about which aircraft is better. I have a soft spot in my heart for the F-23 since I'm friends with the chief designer or configurator for that particular aircraft, but that doesn't necessarily mean that the F-22, is the worst aircraft for that competition between the two. Now, once a design obviously is selected, doesn't always mean that it's necessarily dead, or the losers are dead as well. They can obviously be resurrected with other design changes. Now, another process you can go through is what's called a constraint analysis. And what a constraint analysis does is it starts to bring some physics in to look at some real performance parameters. And so we've already looked at this plot from the Joint Strike Fighter. This was developed by the Lockheed Martin team, Bevilacqua, from the propulsion standpoint, and really kind of focused around that propulsion system and trying to determine what way we can solve this problem. So they looked at these constraints, and these are all physics-based performance lines that you can write an equation of thrust-to-weight ratio as a function of the wing loading, and you end up with these competing performance parameters. The junction of the two allows you to optimize for the conventional takeoff and landing design, and then the direct lift design point for that vertical takeoff and landing option that you have. There are lots of ways that you can construct a constraint analysis. This goes back to an approach developed by Lofton as part of a NASA study, and we'll kind of use this spreadsheet as a starting point for us to allow us to investigate different ways for this particular constraint analysis. Now, what this does, when you have these different equations, it gives you a feasible design space. So you kind of have these areas where you're not designing under the curve or to one side of the curve or other side of the curve. So when you block all these out of bounds areas off, then what you're left with is this feasible design space. And so then you could say, well, any design that meets these requirements that fit within this particular range is going to be good. So it's going to meet our requirements that we have. And so you could say a design up here is just as valid as a design down here. But obviously what you end up with is a system that's going to be over-designed if you're way up here on the top side of the space that has a higher thrust-to-weight ratio in this case than a design down here would. So you'd obviously push yourself down to this lower design space. And here's an example of that for a combat aircraft where you have lots of different curves. And notice some of these curves don't even really matter at the end of the day because they fall under other curves. But you have to make sure that you're looking at all different considerations and options. And then you end up with your final feasible design space. And then your minimum in there is going to be your final design point. So this is what we mean about optimizing your design. You've looked at all these different design variables, and now you can find that optimum combination of these to give you your best design parameters that you have. Now note, none of this kind of really looks at the kind of what that aircraft looks like. These are all based upon equations in here that are really kind of focused on design parameters. It's these design parameters then that you have to make sure are going to be met when you're looking at the details and geometry of your aircraft. Now, there are other operational constraints that you can put in here as well. For example, you can think about a speed of an aircraft on a low altitude mission where you have lots of different parameters that are going to constrain the performance of that aircraft. If you fly too low, you might run into terrain. If you go too fast, you'll get buffeting. If you fly too slow or too high, then you warn the enemy about your particular approach. And so then that determines your operational box that you're going to be in. And so you'll have some area then that you can use for your particular optimization. Finally, for this design approach is what's known as a parametric analysis. And what a parametric analysis does is it looks at, again, different design parameters and runs across a range of those parameters to determine what the impact or sensitivity of one parameter is to another. And we'll do things such as making carpet plots out of these, which again allow us to look at our particular range. So here's an example. This is an impact of wing area on performance for various takeoff weights. So as we're looking at takeoff weights on the x-axis here, we're looking at our various performance parameters over here on the y-axis, and then varying, in this case, wing area. So how does varying wing area change the value or shape of these curves as you go through this particular design process? So it gives you a good feel for looking at the impact, sensitivity, determining whether your relationships are going to be linear or nonlinear between these different performance parameters. Now, a simple way to look at these are to make contour plots. So this one is pretty easy. This is looking at nothing more than lift coefficient. So we're looking at primarily for a given wing loading, what's the lift coefficient that's required to fly at that particular velocity and altitude. So we have velocity on the x-axis, altitude on the y-axis, and then it gives us contours of required lift coefficient. And we know that as we go higher in lift coefficient, our aircraft is going to eventually stall out. So then it gives us a range that we can start to look at and say, well, what's a reasonable range of lift coefficients to fly? So for example, given a wing area of 25 pounds per square foot, particular altitude range that we want to fly at, and a particular velocity, these tell us what lift coefficients we need. And then we can use these to start to nail down our more specific design. Another way to look at this is a set of carpet plots, where carpet plots allow us to look at a range of different parameters and plot multiple parameters on a single plot. So in this case, we're looking at gross takeoff weight, wing loading, and aspect ratio, along with various performance constraints. And so that way, it allows us to run through lots of different parameters and put this in a pretty easy to visualize graph. Another example is called a spider plot. And a spider is a parametric plot, which again compares different geometries. Or you could even do this with one particular design, for example, just to see how it fares overall, looking at different configurations. So in this case, you're looking at your performance parameters for this particular mission throughout your entire mission profile. So starting off with your takeoff and working around through all your different things that you have to be able to perform in a particular mission. So you can, in this case, compare quantitatively and in a graphical format the different aircraft that we're trying to examine and compare with one another. So again, another good way to quantitatively contrast some different designs. In this case, obviously, if you have greater area, that means your aircraft is going to be better overall. Or you could look at a couple different cases where you might have aircraft that perform pretty similarly. These two are pretty close to one another, except this is a morphine aircraft or morphine airfoil performs slightly better than the baseline case. Now, something we've already talked about is benchmarking. And again, in benchmarking, what we're doing is looking at other aircraft metrics from things that have already been developed that allows us to really think about this not just from the physics standpoint, because most of these other methodologies that we looked at in the last few slides are primarily based upon the physics, and they don't really pull into these market aspects that we get when we're already looking at systems that have been designed and developed and put it out into the marketplace. So in that case, that pulls us cost in, which then gives us a better overall engineering standpoint. Now, you can benchmark practically anything. So any of your performance parameters, you can gather that data, put it into a tabular format, and then plot it. and then see if there are any trends. And that's what you want to do with benchmarking, may lie or where your trends may lie for any particular design. So that gives you a good way to make estimates about where your design parameters should be. So here's a good example. This is a range payload diagram. We'll come back and talk about range payload diagrams later this semester. So in this case, we have our range. We're measuring our payload for a passenger aircraft by the number of seats, because we're assuming that every time we put a butt in the seat, they're going to be the same weight for a particular design, or for a particular class of aircraft that we have. So, this is a great way to look at our overall payload. So you can just think about this y-axis being nothing more than a gross payload weight that we have. So what you see is a pretty clear relationship as you kind of move off. There's kind of this axis that moves over, and then you kind of have to use this to make a determination of if you fit something in the middle, right? So in this case, this is a fairly old plot that is being used by a Boeing colleague of mine. So as they were getting to roll out the 777, it filled an obvious niche. Hey, we have this big hole here, right? And so the 777 is going to go in between basically the 767 and the 747 in terms of capabilities. So it's going to fill that gap. It's like, we don't have enough people to really justify a 747, but we could put something here in the 777. Now, they were also using this to make this determination of what should be their aircraft post 777. So they could look at what they were calling the next generation large aircraft, the NLA, way out here, much more seat capability than the 747, or making the what was being called the 7J7, an advanced version of the 737. Now, what they actually decided to do is punt on this. They said there's not enough market for this, and really what's happened with the A380 is actually demonstrating this, and instead going with the 787, which gives us something that essentially advances capability over in one axis, really pushing out that range instead of trying to fill, which is obviously a hole way up here. There's nothing up here, but then you have to think about it from a market standpoint. There's not enough market to be able to sustain the design and cost of an aircraft such as this. And then simultaneously, since this would cost a whole lot of money, they were able to do this and come up with a 737 MAX at the same time. Now, these products, really can make a difference. So you kind of have to think about this in a larger context, and this is going to be beyond a lot of stuff that we really have time to focus on and think about. So here's an example. Our green line here is the number of passengers that are flying on an annual basis. The blue line is the number of aircraft that are in service. And what you notice is this is shooting up exponentially till we get to 1970, and then the number of aircraft actually drop. And that's because we had the advent of these wide-body transports, the 747, the DC-10, and the L-1011, that were being put out into the market. While the passenger growth rate was still increasing, the number of aircraft that you actually had operating in the airspace decreased. And so you kind of have to think about this in that context and how putting aircraft out there are actually going to have an impact as well. Now, a lot of this from an airliner standpoint also goes back to the square cube law that we introduced all the way back at the beginning of the semester in terms of how things are going to grow. If you're looking at purely from a standpoint of putting people on an airplane, then you can start to scale that directly from a volumetric standpoint. Say, how many, seats do I need based upon the number of passengers I'm going to have, and then how is that going to drive my overall wingspan, kind of based upon these conventional tube and wing configurations. And you can make estimates of this all from benchmarking, just looking at data and then pulling up some basic physics based upon these kind of square cube law trends that we have. Now, this has kind of been where our entire airline evolution has been driven from. kind of these smaller aircraft designs to larger and larger designs, and you can see how these things have essentially stayed very similar in overall configuration and what the appearance of that aircraft looks like. And that's because it's a very scalable solution that we have in terms of the wing tube and wing tube configuration. It's very simple. You can, if you need more people, you can scale that up. One of the limiting factors of that is, again, airport capacity in terms of, well, when you get to a certain size, right, and when your tail's span may be bigger than your overall wingspan of an aircraft, then how do you actually deal with the logistical hurdles that you run into for specific aircraft? So you end up with a lot of operational issues that you'll also have to consider. So looking at the NLA or the A380 configuration, for example, how do you get people on and off an aircraft with the FAA requirements to be able to evacuate the entire aircraft in 90 seconds in case of a fire? That becomes very, very difficult to do if you have something like a double-decker. And you actually have to not only design with this in mind, but also at the end of the day demonstrate that it actually works, along with lots of other constraints as well that you may not initially think about throughout the design process. One of those might be operational. Wake vortices is a good example of that. These regulations are dictated by the FAA based upon a ratio of a leading aircraft size to a following aircraft size. And this may not seem like a big deal, but it has a direct impact on the capacity of an airport. Meaning as soon as one of these jumbo jets takes off, you end up having to wait a lot longer before you can put another aircraft in the air from that particular runway. So these do have impacts that may live a lot longer than these design decisions that you kind of make early on in the process. Now, for these benchmarking, I do encourage you to go back and look at these mission-specific, kind of market survey-driven types of things. The more data you get, the better. Hopefully these will be able to tell you some trends that you have. You sometimes may have to make engineering decisions about, well, which line do we actually want to fall on, when I have a lot of scattered data. So there may be some details in here that aren't necessarily popping out through a simple analysis, while other times dead on, they'll be really useful from a design standpoint to be able to say, yeah, this is great. This is going to tell us exactly where we need to be in a, say, open niche. Yeah, we have pretty good confidence, that if we picked a design between these two in terms of number of passengers, what our overall takeoff weight is going to be if we're using the same design concept and methodologies, manufacturing for all of these particular aircraft. Again, you kind of have to look at this from that standpoint of, is your design fitting a niche that isn't being solved, or is it doing something better that a current design out there is doing right now? If you can't answer yes to one of those questions, then you really have to question whether your aircraft design is actually going to work. And that was the strategy that Boeing took when they were trying to make that decision about whether they're going to pursue the NLA or the 787, and again, looking at the basic data that they have. And what they decided was, what we can do is take the 787 and then at the same time, go back and look at our 747 and see what we can do to improve the seating capacity on those. Now, from a market survey, again, what I recommend that you do is look at lots of different aircraft competitors that are out there, things that are going to be mission specific. Look at the special requirements for your particular aircraft design that you have to do, and then put as much data together as possible. There are a lot of sources out there, some things online, some things you have to look in a book, but from that you can then use that to help drive some of these not only gaps that you may have in trends, but also to help drive some of the performance parameters and design parameters that you may need to put into some of your software that you have. Examples of those would be, when we're trying to use a program such as Iterative to be able to predict what the lift to drag ratio is going to be. What should we use, right? What value should we use? Are we just going to pick something, based upon one of our equations, or, are we going to rely on data that we have that's out there that's going to be much more grounded and give us much more confidence that the value that we're using is good. Again, looking at our airline market, comparing both regional jets, jumbo jets, wide body aircraft, and turboprops. You kind of have a bound here between 10 and the low 20s for your aircraft. Pretty solid average right around 15 for your lift to drag ratio. And you can see there's not a whole lot of improvement over time. Notice that the 777 up here stands pretty high compared to some of the other aircraft. There's only so much you can do, in terms of finessing basic design parameters. So this aerodynamic efficiency is a great driver, for your performance of the aircraft. But, in something like an airliner, there is going to be an upper bound, an upper limit that you can use with a conventional design. Then you have to start thinking, well, if I really want to try to push the limits of this over to here, I got to change how these things are laid out to make this aircraft look a lot more like this one. What can we do with things such as the engines to be able to make that actually happen? Same thing for structural efficiency. This is operational empty weight over mean takeoff or maximum takeoff weight. Again, you can see kind of an average around 0.6 or so, with some clear delineation between the different types of aircraft that we have. Turboprops obviously being a little bit heavier than our other aircraft. And then same for propulsion. Notice in propulsion, there is a clear trend. Here we're looking at thrust-specific fuel consumption. There are clear improvements over time. So we've done a lot better job at improving the fuel consumption of aircraft over time, making them more efficient as we've improved our engine design. You'll also notice that there's clear delineation here, which you see much clearer than some of the other benchmarking plots, where turboprops have a much lower thrust-specific fuel consumption than the jumbos or the wide bodies and the regional jets. So this is a clear driver to say, hey, this is going to be kind of a greater fuel consumption than maybe a regional if you're thinking about competing with one of these two. As we mentioned in class, one of the drivers for having these regional jets over turboprops, these tend to have a little bit of a speed benefit, but they also have that benefit of looking more advanced, and so they have a market component where the customer feels like they're getting a more advanced aircraft using a regional jet over a turboprop just based upon appearance alone. So we'll end there with this one. I'll pick up with some sizing examples on how to size aircraft in a separate lecture.